Well, good morning and welcome to the celebration of Faculty Careers Colloquium. Claude Kokini, the Associate Dean for Academic Affairs, is usually the host of this, but unfortunately he isn't here today, so it's my pleasure to be able to talk about our speaker today. Just to give you a little bit of background, this Colloquium of Faculty Affairs grew out of the College of Engineering Strategic Plan, specifically the Faculty of 2020. And through that program, full professors get a chance to tell us about their accomplishments. We get a chance to learn about what they have done over the years. And then they also have an opportunity to plan for what's coming next. The full professors of at least 7 years was task promotion of full professor, speak to a group, and then they work with their heads and with the dean to look at what they can do next for us, as if they haven't done enough already, right? So today our speaker is Professor George Lee. He's a professor of electrical and computer engineering. He finished his PhD here at Purdue in 1978, and he's one of those outstanding graduates that we didn't let get away. We've kept him. He's been here the whole time. He's a fellow of IEEE. He has won the IEEE Third Millennium Medal Award. He's got a Distinguished Service Award. There's a whole long list here, but rather than spending time talking about those things, I think I would like to turn it over to him so he can tell us about human-centered robotics. Professor Lee.
Thank you. Yeah. Thank you for a very nice introduction. First of all, we need to decide whether I should present or let the robot present. So what I want to talk about is human-centered robotics, meaning the robots that are either in the human form or non-human form that kind of collaborate and interact with humans. Okay. So I'd like to start saying that I started my research since 1974 when I was a graduate student. I focused on several topics, but in this talk, I'd like to maybe just focus on 3 things: robot manipulator, neurofuzzy systems, humanoid and human-centered robotics, and then I'll finalize it with some future direction talk. Okay. So this is me, long time ago, young, energetic. And this is my former advisor, Professor George Sarides, and this is what they call the MIT robot or MIT arm. And at that time, it cost about $14,000. And my PhD focused on this robot, connect that to computer, and implement a control system for it. Okay. So since then, I graduated, and I work on the Puma, which is a commercial version of the MIT robot. And I was fortunate to produce a lot of PhDs in all these areas. So focusing on kinematic dynamics control, adaptive control, visual surveying, okay, sensor fusion, etc. And this is a partial list of the paper publication. You can see that actually this paper was published at University of Michigan, and at that time there's no textbook. A lot of people use this paper as a textbook. And if you go to conferences, they will say, "Hey George, I learned everything from you, from this paper," and all that kind of stuff. And also, this is one of the nice papers, is a visual surveying, one of the earliest paper. And I think John Fellmer is with the St. Dears National Lab, and he's a senior manager. I also write a book, since there's no textbook, and the book was translated into 5 different languages in addition to English: Chinese, Japanese, Russian, Spanish, etc. One thing I found out, that writing textbook does not make you rich. In addition to writing papers and books, I also fortunately get some money from NSF, and I was able to develop a senior capstone lab, and I was getting about $80,000 from NSF and $80,000 from the department as a cost share. And what I did was buy several robots, the Puma robot, and for undergraduate students. And this one has about 5 workstations, and focusing on these 5 topics: understanding robots, sensing control, AI and robotics, material handling system, and then a project. So this one is for the AI, basically playing tic-tac-toe. So you have a computer vision on here, camera, robot is around here, and then play the tic-tac-toe with the robot. This one is a project. You can see that a group of students working on this project. They have 2 robots, one in here and one in here. This robot kind of placed object on the conveyor belt, and then the object will be moving towards this end, and then the other robot will come and pick it up and put away. So it's simulating the material handling system. Okay. So that kind of worked for 10 years. And after that, stop. I don't know what to do. Because the robot kind of not really smart, moving repetitively, and is really structured. And if you want to work on it, you need to put a feeders, you need to do a fixture machine and all that kind of stuff. So how are we going to make the robot smarter? So at that time, there's such called as a fuzzy logic control system. So I have a very, very good student. His name is Chin-Ten Lin, okay, or C.T. Lin. That was 1988, he came to me. And actually, he was accepted by the University of Michigan, but he does not want to go to University of Michigan. He wants to study under me. So his advisor called me up and said, George, my best student was accepted by University of Michigan, but heard nothing from Purdue. So I went down to the graduate office and find out that they have not processed his application, because at that time there's a 3% quota. So I went down and looked at his application. He was ranked #1 from his class. So I gave him an assistantship. And he came, and it turned out to be my best student. So he came in, worked on robot for 1 year, got his master's degree. Okay, and then he wanted to continue for PhD, and he wanted to work on robotics. And I told him, wait, let's stop. Let's think about some other thing. So at that time, all these things is a fuzzy logic control system. So what is a fuzzy logic control system? It's a very, very simple idea. It is a mapping from input space to output space. So consider you have a cluster of data in input space and a cluster of data in output space. To relate the input to output, you have if-then rules. Very, very simple concept, right? It's a rule-based system. Then, in 1965, Professor Lottie started developed this fuzzy set. It's a famous paper, it's a seminal paper. And then in 1975, there's such thing called fuzzy logic control using the fuzzy set. And basically the idea is that try to control a plant, you use a fuzzy logic control. You have an input, you try to fuzzify the input, go through the fuzzy rules, and then defuzzification. So what's the meaning of fuzzifier and defuzzifier? So let me give you an example. So let's say if you want to control Google car. A lot of people talk about Google car, right? So let's say if you're trying to control Google car, there's 3 inputs: speed, acceleration, and distance. So for this speed, I measure the current speed, right? And then you have 5 fuzzy sets. Okay. So this fuzzy set represents the clustering of data. So if we measure this present speed, this present speed touches 2 fuzzy sets, too slow at 0.2 and slow at 0.8. You have acceleration, you have 3 fuzzy sets. The present acceleration touches the decelerating at 1. You have a distance, and it touches the close at 0.5. So they have a rules. So how do you execute the rules? They say if speed is too slow and the acceleration is decelerating. Speed is too slow is 0.2. Acceleration is decelerating is 1. The end is an intersection. So it's 0.2. So this rule is fire. When it's fire, it increases the power greatly. Increase the power greatly at 0.2. You take this area. You execute these 2 rules based on the input. You get 3 areas. And the output, you can take the centroid of these 3 areas, and this is output. So what's the problem? The problem is how to design these fuzzy sets. How to design these rules. Okay. Then come my student, C.T. Lin. He looked at the neural network because I gave him the topic. Take a look on the fuzzy logic control system. Take a look on the neural network. Can you come up with a system? Okay, so he come up with this. Learning, speed, acceleration, distance. You can see that speed, 5 fuzzy sets. Acceleration, 3 fuzzy sets. Distance, 3 fuzzy sets. From these input, you have rules connecting from input to the output. The output has 5 fuzzy sets, and then the motor power. So what it means is that he has developed an isomorphic system from a fuzzy logic control system, from a design to the training of the neural network. Okay, so you can see from the input to the output, there's 5 layers, and they're identical to all these. So this is a paradigm shift from a design problem to the training problem. Okay, so he wrote a paper, neural network-based fuzzy logic control and decision system as a student member. Okay, and that was 1991. And then he graduated in 1992, and then after he graduated, he also wrote another paper. And afterward, he kind of tricked me into writing a book with him. So we wrote another book, and so this is a kind of 96. So I kind of, every 10 years, I kind of write a book or something. Okay. So fortunately also, I like to thank that because of the Engineering Research Center gave me some money, and I was fortunate able to continue to do all this research. So after that, there's a student that say, I want to continue to do neural fuzzy. So I look at it and say, well, why don't you do this? This is what CT-Link has done. It's doing a feed-forward. Why don't you make it dynamic, meaning you put a recurrent network in, so that when you put a recurrent, you put a memory in, then this system is a dynamic system instead of a feed-forward, which is an algebraic system. So he put the neural network and put a recurrent network, a memory inside, so then the whole system becomes a dynamic, and it can describe a dynamic system. So with that, I was looking for money, and I was fortunately able to get some money from NSF from 97 to 99, kind of collaborate with a professor in University of Hawaii. So he has an underwater robot called Auden, but he really running out of idea how to control it. So what we did is that we teamed up and wrote a proposal to NSF, and he got his own money, and I got my own money. And the idea was that to get the input, output to the underwater robot, to train this recurrent neural network. And so the torque going to the robot, the position and velocity feed into the input, and this is the output, and you measure the error, and then you try to keep on online learning. So from this, we need to collect the data. So I was happy that I was able to spend 2 weeks in Hawaii to collect the data, but I let the student do the collection, and I was in the beach or something. So we move around. So this red thing is kind of a safety to make sure the robot does not hit the bottom of the swimming pool. It's not outside the ocean. It's in the university swimming pool. So what we have done is that we have woke up in the morning like 5 o'clock, perform the experiment, and then they have cleaned up the pool to open like 7 o'clock or something. Okay, so what we did is that basically is that move around, take the input and output data of the robot, and using that to do the training. And so we come up with 2 control algorithms. The first one is that after the training, then you do the control, and you use a proportional derivative control, and this one is fixed after the training. The second one is that after the training, we still continue to train. That means online learning. And using that, we were able to publish the paper, and the result, you can see that if you continue to learn, the error will decreasing. However, if you just do the training and then stop learning, then the error kind of very, very steady. Okay? So that was, again, 10 years. I got a pause. What should I do? I know something about robot. I know something about neural fuzzy. What's the next step for me? So it seemed to be always around every 10 years, 12 years, one have to sit down and think about your research. Right. So fortunately, in the summer of 2000, I got a call from a friend of mine in Japan and say, George, are you free to visit us for 2 months all expenses paid. So I was so happy, I said, okay, sure, I'll come. And that was from the University of Tsukuba, which is about 45-minute train from Tokyo. And next to Tsukuba is a famous lab. It's the National Institute of Advanced Industrial Science and Technology. It's where the most of the humanoid robot was developed. Okay. So I spent there for 2 months, and I was an employee of a Japanese government because the university is a government's pay. So I'm a Japanese, so I could not get out for that 2 months. It's all stay in Japan. So that is the first taste of humanoid when I was there. So that summer, there's a big exhibition in Tokyo. So I went there, and I saw Honda have a big exhibition. P1, P2, P3, kind of from a biped. That means there's no upper body, just walking. So I found out that Honda, way back in 1993, they started to work on a biped. In 96, they introduced the first humanoid robot in a conference. They call it Honda Robot. It's this one. It's about my height. Okay. And if you look at all this gear, it's very, very sophisticated. So by looking at that, from that on, I feel that I love humanoid robots so much, I should get involved in humanoid robots. That was the idea that hit on my head that this is the robot that I should work on. At the same time, I visit a lot of university, and this is Tohoku University. There's a PhD student who built this one from scratch. And his thesis was try to walk this robot on the conveyor belt. Okay. So there's some other interesting robot. There's a 2-arm robot from Fanuc. It's a very, very large company in Japan for industrial control. There's an industrial robot from Tohoku University, 2-arm robot. They just look at this 2-arm, and then there's a mobile platform. Or I think some of you know what is a Sony Play Dock, right? They discontinued that. This lady was talking about the NEC robot trying to do talking to a robot and turn on the TV, turn off the light, and all that kind of stuff. And at that time, they were talking about selling this robot for $100. And I didn't see it coming, so I don't know what happened. Okay, so I go back and think about myself. This is what I have learned. This is what outside in the market. So I really need to work hard to really go from this knowledge and generalize it to these. So what I did is that I fall in love with humanoid. And then I look at it, why do I like humanoid? Because humanoid is nothing more than a mechanical cloning of a human. So you can think about put the brain into the humanoid, put the arm, put the legs, and all that kind of stuff. Can we build a humanoid like a human? Okay, so there's a lot of research, collaborative research, that one can work on it on the humanoid robot. So, some open questions. How to make humanoid robot behave like a human? Walk like a human, think like a human, collaborate and interact with human. So these are the key points. So what are the desirable capability and functionality? Locomotion and control, mobility, sensing, perception, cognition. You want to understand the environment, to understand the human that you work with. Coordination, communication and control, autonomy, and human-robot interaction. Collaboration and cooperation. So these are the desirable characteristics that we want the humanoid robot to have. So after coming back from Japan, I keep thinking about it and finally writing several proposals, and finally I got one funded. That is the last ITR proposal. And I got this one is probably close to about $1 million, $960,000, something like that. And it was with Howard Zelansnik. And the idea was how to skill learning, meaning how to transfer human movement or human skill to the robot. And so continue on that. I also received another one that is from 2009. And basic idea is how to transfer the human movement to the robot and etc. The key point is that human has about 150 degrees of freedom. This robot has about 38 degrees of freedom. So there's a mismatch of number of degrees of freedom. Okay. So after I come back, I set up this lab, and I kind of focusing on several important items. The first one is that try to understanding purely go on the perception and cognition. Try to make the robot understand the environment, to understand with human and all that kind of stuff. Second group of people are mainly working on the hardware, on the control, mobility. I also have some education outreach activity, and then another group is working on autonomous vehicle, mobile robots and all that kind of stuff. So hopefully this will be kind of a more complete approach to a humanoid robot. So take a look on, this is an old tape. This is how the humanoid walk. That was probably way back in 2005, something like that. You can see it's bending the knee. Humans don't walk like that. We don't bend the knee and walk. But bending the knee to walk is more stable. Because actually, this is a singular position. You can fall down, fall back, and all that kind of stuff. But human is very, very good because we learn how to walk since we are age 1. Right? So that kind of all implemented into our brain. But in here, you can see that it's all bending. Okay. So I have a graduate student and look at it and say, maybe what's the best idea is how to generate the human-like whole body movement and put it to the humanoid. So how to generate all these human movement? Take the humanoid model, put into the library, and put it back to robot. Okay, so the idea is very, very simple. And what we did is that I collaborate with some professor in kinesiology. It's a Professor Shelley Riddick. He has a motion capture system. So we use that and capture the movement, sensing, take all the trajectory, take the model, and then manipulate it, and then put it back to robot and see whether the robot can walk. And obviously, one can see that kinematics play into play now, that convert all the angles, orientation, and put it to the robot. And what happened? The robot falls down. Okay, because there's a mismatch. Okay, from the human movement and the robot movement. So then we have to go back and look at the stability of the robot, and you can look at the stability of the robot. Basically, we are always looking for the center of mass. And from the center of mass, when we walk, the center of mass had to be on the supporting plane. And once if that is not true, the robot is going to fall. Okay? So based on that, he kind of fine-tuned the trajectory and come up with so that all the trajectory were in the 0 moment point. And so it works. Okay. Then after that, now my student, Andy, is here, is that feeling that the whole body movement is very, very complicated. Why don't we break it up into upper body and the lower body? Why do we think about it? Because if we look at the movement, let's say this baby, right? This child, you can see that when they do something, it's usually it's upper body, and walking, lower body. It's very, very not usual to have both things working together. Only when you play sports, basketball, that you have the whole body. And so I just don't think that the robot can play basketball at this time. Okay, so maybe it will be easier for us to break into the upper body movement and the lower body movement, and then merge them and see whether we can do a manipulate task and all that kind of stuff. So while I'm working on that, then some opportunity come up, and we were able to get the MRI R2 grant from NSF, and the Drexel was doing that, and they received $6 million and was able to buy, I believe it's 6 humanoid robots. So make a guess, how much is this humanoid robot? Make a guess. My house is less expensive than this robot. So this robot costs $300,000. $300,000. Okay. So we bought 6 and they give to some of the universities, and at the same time, we use this robot to attract the DARPA grant for the DARPA Robotic Challenge. Okay. So maybe let me talk about this and then we can do a demo. So the DARPA Robotic Challenge event is basically because of this tsunami in Japan way back in March 2011. They tried to use a robot and found out a lot of robot was not able to perform the task. And so they kind of see what kind of task that a robot should do in a disaster site. For example, get into the vehicle and drive the vehicle, walk on uneven terrain, moving debris, opening the door, climbing up the ladder, breaking a wall, maybe opening or shut the valve, and put the pump on or off. So these are the things that they think about the 8 events. So in our team, we have so many universities participate, so we kind of divide the work. And Indiana University and Purdue University focus on the ladder climbing. And I have some video to show that. So before I do that, I think Andy wants to show how this robot moves. Okay.
So as Professor talked about transferring human motion to humanoid, right? There's a mismatch. So we had our algorithm running so that we can adjust human motion to work with the humans. So this is some of the demos that. So you transfer the human whole body motion and then adjust for the human motion. We have some famous dancing.
Oppa Gangnam Style. Oppa Gangnam Style.
You're going to do some walk?
Some locomotion as well, but I think he can talk about it a little bit as I prepare.
Okay, yeah. Okay. So, thanks, Andy. So we team up with Indiana University. So it's kind of unusual that we fight each other and then in this project we kind of work together. So it kind of funded 2 students from IU, and then it's my student Andy, and then Manis is here. Okay, so we have almost 4 students. The idea is try to climb the ladder. So we have the first 6 months, we have some sort of a forced start. Because the IU, they are doing motion planning, and Purdue is supposed to do the control. So first of all, IU proposed, why don't we use a rock climbing strategy to climb up the ladder? Then I think about rock climbing is that you really use both hands to lift your body up. And sometimes you need to use the feet to lift yourself up. So based on that, I say that is not natural because the robot, that means you're going to break the weight in here. So the whole weight is pretty heavy. This one probably 150 pounds or something like that. So climb up to that. So we say maybe that we should not do that. So I start looking at the papers and and then I ask every student in my lab and I get a ladder and everybody to climb up the ladder and tell me how do they feel about the ladder. You find out that you really don't use the hand to lift your body up. You use your feet to walk it up. And so we start to look at some papers, and biomechanism people, they look at that and they say that they have performed a human experiments and that actually they are looking at the human center of mass. And if you look from the back, actually when we walk or we walk up the stairs, the center of mass moves to the right of your foot and you lift it up. And then when you walk, your center of mass moves to the left and you lift it up. So you can see the center of mass move to the right, lift up, and then the center of mass move to the left and lift up. So actually, ladder climbing is very, very similar to a stair walking. If you think about, so everybody then will walk the stairs, and then if you look at the walking the stair, it's similar to the ladder climbing. So I told the IU professor, say, let's walk up the stair together, and you tell me whether we should use rock climbing or ladder walking. And I convinced him that let's do the stair walking and using the backward. And why is it backward? Because the backward so that your knee does not hit the ladder. Okay, so it's kind of a little bit not like a human walking up the stairs and all that kind of stuff, but it's basically it's an engineering approach. So I forced Andy to work out all this state, the contact state, 2-point contact, 3-point contact, and all that kind of stuff, and then work up the finite state machine and find out the procedures and all that kind of stuff. And also we need to look at the center of mass and all that to make sure the system is stable. The summation of forces at the center of mass have to be equal to 0, and then the moment have to be equal to 0. So at every state of the contact, so they have to be all equal to 0 and all that. Of course, I mean, mathematically, it's not going to be equal to 0 because of measurement error and all that kind of stuff. So we did not use this robot because this robot is too weak. Okay, so they redesigned a newer robot and have a 7 degrees of freedom. It's a little bit stronger on the arm, and they call this a DRC Hubo. And this one is a Hubo 2+. So what we did is I do a lot of work in the lab. They did a simulation. So you can see that the center of mass of the body, okay, and this is the center of mass, and it's right on the foot. And you can see the body move, okay, move on the feet, then you move to the right or to the left of the robot, and then you lift up so the center of mass actually is on the foot. We also performed the experiment, and I took my wife's stepping block and that and put it in the lab and let them play around with it. So that it's like go up, just one step, okay, and very, very carefully move it, right, and then see whether they can backward and step it. Same time, I think they moved the robot outside their room. It's an EE51, and they were able to step on it and move up just one step, because I just want to prove the concept. I don't need to. So this is just a stair walking. It's not ladder climbing yet. Okay. So then later on, let me finish this one. Okay. And so later on, then they go to the summer. Two of my students went to Drexel, and then they have this robot. They did a simulation again. They work at Drexel, and then this is about, I think, 10 times speed. And then when they come back, then the robot was in Drexel, then we use the internet, connect it, and then do a teleoperated, and then the IU, they look at the simulation, and then they try to make sure that everything is working. Okay, so we did a lot of testing, a lot of verifications and all that kind of stuff before the DRC competition. So that's actual competition. So this is in Miami last December. So they are walking up already. I think up to here, they already scored 2 points, right? So in here, it's already scoring 2 points. Together, it's 4 points. So you can see that they have head, reverse it, and they have something of a hanging, so make sure the robot, if they fail, it won't crash and all that kind of stuff. You can see that very slowly, backward, climbing, and there's a reporter there. And if we were successful for this one, it would be the first robot to climb it. Okay, so now you can see that the footstep is kind of a little bit way off. So they make a fine adjustment. And this step, this is off a little bit. This is way off, and it fell. So because the motor control is very, very sensitive, and also on whether it's a flat, because of flat feet. And so unfortunately was not able to, but then when they doing the experiment, they were able to finish the whole thing. And also because that day there was because there's a computer vision did not see this handle is not very, very good because of a segmentation problem and all that kind of stuff. Okay, so based on that, then I have a graduate student. What I'm doing is that using the Kinect, try to mount it on the top of this, on the top of the head in here. So try to mount a Kinect and try to recognizing the human pose. And then from the human pose, we try to recognizing the human interaction. So that has a lot of application. Monitoring, surveillance, homeland security, all that kind of stuff. Okay. And what we're going to do is that recognizing the 15 points from the 3D point cloud, try to represent it based on the limb location and all that kind of stuff, and see whether we can identify some human interaction activities. And this is ongoing, and actually this one is co-sponsored with, or co-supervised with Professor Chen Kok Ko. And I'm going to extend is that if we're recognizing the human pose, can we detect the fall of a human? And this is a very, very important application or theoretical study. Okay, that is when human getting older, our body kind of getting stiffer, and it's easier to fall. This is exactly like this robot. This robot is very, very rigid now. And so what we're trying to do is that can we detect the fall? And I'm going to actually, this afternoon, we're going to have a meeting with some professor from health and kinesiology, try to discuss how to detect and prevent the falls, and then how to control it and all that kind of stuff. Okay. And I think there's a graduate student, Yang Guo, is here, and she's going to be working on it. And she is from mechanical engineering. So we also have done some outreach activities. There's a lot of high school kids. They enjoy watching the humanoid robot, playing with robot, the robot kicking the ball and all that kind of stuff. And I want to highlight one activity, and this is our Yiyu Student. There's a research for undergraduate students from NSF. And this is purely built, this case or this platform is built by the undergraduate student. And what he wanted to do is to do a DDR, the Dance Revolution. So let's see the video. So he built it, he used a camera, look at the screen, and then move the robot. And this is all done by an undergraduate student. It's a Paul Feddersen. Okay, and this is only one summer, I believe. Okay, and this is what the robot seeing from the camera, and this is what the robot, that we put the input to the robot. Okay. Left, right, and all that kind of stuff. This is a real time. It's not, right? I mean, it's not, we did not speed it up. So this is a real time. And this was also, IEEE Spectrum quote this story. So very good. Okay. So, future research, what's the direction? My thinking is that it requires a lot of vision, creativity, innovation, and imagination. If you look at the current research, the trend, cloud computing, big data, brain initiative, sensors and electronics, energy. So where should I put the robotics? So a lot of people talk about the Internet of Things. All these little things connect together, prosthetic devices, iWatch coming out maybe, or it's already arrived from a Samsung. Computers, Google Car, Google Glass, iPad, iPhone, and this is the wearable helmet. That is an important thing. And I think the future robotics is in this one. The brain-computer interface to control the robot, to control the prosthetic device, to control the automobile. So what do I mean by that? So let me introduce my former student. This is Professor C.T. Lin. This is a group of his students working on this brain research center. Currently, he's getting about $800,000 per year from US Army doing that. Doing what? Doing the brain-computer interface. So if you look at the brain-computer interface, meaning it's trying to extend the capacity of a brain in communicating, interacting directly with things. So what are these things? Robot, anything that you can think of that can be controlled by the brain. So there are two types you can think about, the active and the passive brain-computer interface. Voluntary control and then the passive. So in the voluntary control, you can use an EEG to do a goal or intention control. Or you can use an EMG for prosthetic limb control. Okay? Passive BCI is that you try to measure the brain wave and then assess what's the mental condition of the person. So for example, driving, you want to maintain and see what are the drivers. Is it alert or it's not alert, or is it drowsiness? Maybe you want to use the active BCI control. This is a CNN report to control the wheelchair. And then the Japan and the French company or the research lab, they have a joint robot. Now, all these is a helmet, but this BCI interface is a wire, and it's a commercially available. So what they are doing is basically is to measure the brain wave and then try to control the wheelchair, try to control the robot. So my student is slightly different. He's doing is wearable, it's wireless. It's one step ahead of all the other people's doing. So what he's doing is that he actually, later on I'm going to show you something. So actually he's trying to do is that to have several channels to measure the brain wave and then try to see, to measure whether the mental state of the human brain and then maybe using the device to control other things. So he was trying to tell me that he has one paper that is in the IEEE Assets. It's a #1 highlighted in the 3.5 million publications. So it's a highly referenced paper. So let's take a look and see what they have. So this is a MIDO, 64 channels. So basically they try to say, it's really you don't need to prepare the head for wearing the commercial one. This is what they built, okay? And this is under the US Army. Just plug it in, and then they try to measure 64 channel. Testing the signal. So you can see that all these channels kind of coded. So Andy, so let's take a look on the next slide. So this one is trying to get rid of the noise. So this is a PhD student. So what he's doing is that he's wearing this one. It's a MIDO 32, not the 64. It's an older version. So that when you wear it, when you move it, and something, you're going to generate noise. Okay, so they already built in the signal. So these are the noise that when you hit the helmet, so they filter it, and this is a clean one. Okay, so I asked him the other day, and he said that they built in a high-pass filter and a band-pass filter inside that to filter the signal. So there's a lot of research going into that. They built their own. So it's not buying from the market. So it's just shaking and all that kind of stuff, generate the noise, but eventually you still get a very, very clean signal for processing. Okay. Okay, because of time, or you want to go? Andy, are you going to still show the walking?
I think after residency, the connection became a little unstable.
Okay.
It was walking too well.
Okay, so let's take a look on the next slide. So this slide is kind of interesting. Is that when you measure the signal, do you know where the signal coming from? So you kind of trace back the source. So it's a source localization. So this is your brain, and you're trying to, from your measurement, can you backtrack and see where the brain, and then try to connect the dipole that in the brain and then see where they're coming from. So it's kind of reverse. So in the forward, you measure the signal. And then after the measuring the signal, can you trace back where the signal coming from what sources? Okay. And so this one is also interesting. This one is using mind to only 4 channel. So he looked at arrow, and the person had to be concentrate, really think about it, and then force the output to be in which direction. So if you see an arrow on the left-hand side, you need to force it to the left-hand side. Maybe I should repeat that again. Maybe I should repeat that again. That's it. So you can you maybe start it, Andy? Yeah. So you can see right, left, and then he kept the score on here. So at this time, there's only 2 output. So even if you can, I was kind of curious why you can use a 2 output to control the robot. So in a sense that they try to use like a binary tree, hierarchical structure. Left, right, and then the left, right, and then the left, right. So if you want to control several things, you first of all pick the first one first, and then go down to the next level, and then you pick the next one first, and then you pick the next one, and going down. So he was saying that even you going to the 4 output is very, very difficult. So it's really improving, okay? So this is what I like. So what they have done is game playing. So they have a two person from UC San Diego, 2 person in Taiwan, and then connect through the cloud. And then they try to, what they're trying to do is try to do a concentration and to move the ball. And who has a better power or brain power to move the ball or something like that, okay? And it's very, very short. Probably you can restart that again. So if you remember Return of the Jedi, right? I mean, you try to move the airplane up and all that kind of stuff, that force. So it's measuring the brain and then try to move the ball and who is going to win and all like that. And the key point is that using the technology of cloud computing from US to Taiwan. So I thought what he's doing is really interesting and will help a lot of stuff that what we're doing at Purdue. Okay. So what he's trying to say is that this is what currently people wearing these and the cables and all that kind of stuff. What he had developed is a wireless wearing. And I thought if he had formed a company, I think Google would have bought his company because Google really need this kind of thing if they want to complete their system. So it's a wireless EEG system. So in the future, he's trying to include the cloud computing, big data, and all that kind of stuff into the system. So in summary, new generation of robot require integrative, multidisciplinary, broad-based research and education. I did not touch anything about the social impact and ethic issues. A lot of people think about the military robot and all that kind of stuff, and I don't want to touch that because the technology is going to push in that direction no matter what. Okay. What the current application, manufacturing, search and rescue, space and underwater exploration, military education, etc. Desirable characteristic, as I mentioned, mobility and autonomy. You need to put the intelligence to the robot. You need to perception and cognition. You need to collaborative and you need to interact with the human and the environment. Okay? And obviously, I'd like to thank all the research money that was since 2000. And the 2000 before that, I did not list it here. So from an NSF grant and from a DARPA. And I'd like to thank the work that done by my current students, right? And then I have produced about 26 PhD students and 8 MS students. So thank you. So if I still have time, probably you can take a look on this one. I was thinking because I run out of time. That is also from my former student, the CT Lin. So they mounted on the person, okay? And this is a virtual reality. They put the screen, and this is not the actual car, but this is a 6-degree steward platform. So it's simulating the driving. So they try to test whether the driver is drowsiness or is alert by measuring the brainwave. And this is thinking about what the brainwave is, what is alert, and this is drowsiness. And then when the drowsiness, when they come up to one, and then they're going to hit the person, and that will come up. So this is very, very useful. That's why I think the next frontier in robotic research is the brain, is a brain, is a brain, and how the brain is going to connect to the robot. Okay, so I think that's all I have to say. Thank you very much. I'll be happy to answer any question. My son is here.
So I have a question with the challenge. You said that when the robot was climbing backwards, just before it hit the top step, clearly the foot was a little off, and that's why it fell over.
Right.
Now, is there any feedback loop that actually senses where the foot is? So because you could integrate that and form a loop, and you could do correction.
Yeah.
Is that part of the? Was it not there, or can you talk?
It's a very, very good question. Okay, so we have a force torque sensors on each foot and on the hand. It's only 3 degrees of freedom. And actually, I want to put in 6 degrees of freedom. But even 3 degrees of freedom should be enough. But however, because of the timing, because the DARPA purposely put a very, very low bandwidth from that robot to, they control it through a trailer. And that is mainly they want to see that how can you do like teleoperated. So for the first trial, they try to do it somewhat semi-autonomous, not fully autonomous. I think in the final, next year, they're going to do it fully autonomous.
So in that case, you could do a local correction.
That's right. So then you can measure the force torque sensor, you can see where you're stepping on, and maybe even you put the camera and see where the foot and that feedback.
Actually, the point I raised is also related to when you said you actually take human movements and essentially map them as inputs for a robot, and that's how you do the Gangnam style.
Right.
But there again, you can actually wrap a feedback loop around it and say that,
Right.
look, when, for example, I saw a couple of times it hit its own body, right?
Right.
So that you should maybe avoid it a little.
Right.
And so
Right.
that's probably always an end goal, that you make it
Right.
a bit more
Right.
robust. In that
Right.
sense.
And also, some of you probably recall the Asimov fell down on the walking the stair, because everything is open loop. There's a curtain. Behind the curtain, there's a lot of people controlling it offline and transmit the data to that. And so when you have a step, it's a little bit taller or something like that, the Asimov is going to fall. It was an embarrassment on that. Right.
The other thing is, it's kind of interesting that because the knee is always bent forward, you climb backwards, right? Is everybody doing the same thing? Or because it's a competition, I imagine there are other people doing the same thing.
Right. The Japanese also did the same thing as what we did.
Backwards.
Backward. But then they are even more advanced. They request, because they are wider, they request the handrail to be taken out because it was blocking them. So they just walk.
So no stabilization.
No stabilization. But the concept is the same, right? It's exactly, they say that, hey, if I can balance, right, if I can balance it, but all the Atlas, okay, the Atlas robot that is by Robot Dynamics, not the robot, so Boston Dynamic, okay. Google bought them, right? That one has an Atlas, which is a pneumatic, okay, it's very, it's a hydraulic, and it's very, very heavy. And
power consumption, huge power consumption.
That's right. They did it in the forward, and nobody was able to climb beyond the second
Did you use
step.
a lot of hand motion then?
Right.
Did they pull themselves up?
Right. Both.
Yeah.
Both.
Because,
And they also use a hook or something, yeah, to hold.
So when we climb, right, so I think we tilt forward, right? So that's one way we control the...
So you tip forward is also because of your center of mass,
So
right?
that's how we control that's how we are able to not necessarily bend our knees forward, right?
That's right.
So
That's right.
all kinds of interesting.
Human is really good at avoiding the collisions. The robots, we have to deal with a lot of competition. So if you climb backward, you can avoid that.
The other thing is, the reason why we stand straight is that we are constantly adjusting, right? If you've had some inner ear problem, you can't stand straight. Then you probably have to walk like a robot, bend your knees. But that's one thing that we actually, there is a constant feedback loop
Right.
going on in the humans.
Right.
And this,
So that thing I want to address is if you're getting older, when you walk up the stair, you need to hold the rail, because the sensing is worse, your control is worse, right? when you're young, I don't think you need to hold the rail.
If you're
So
doing the
that's feedback.
breakfast club, if you're young, after visiting a few bars, I think you still have the impairment, right?
Right. Right. So there's a lot of interesting things on. So I feel that the humanoid is very, very interesting. It may take a while to be useful, but still I think DARPA was really looking at that. And I think the future of the humanoid will be search and rescue, space exploration, undersea. You see all these, they could not get, trying to image and all that kind of stuff. So I think that, yeah.
When you're doing search and rescue, you're in very extreme environments. Sometimes it's it's very dusty or
Right.
wet. Or,
Right.
I mean, I can't imagine this guy does too well when he's in rain.
That's right. That's a
And
very good point, yeah.
what-
So,
what kinds of things are we doing to make him able to withstand those kinds of environments?
so that's what the Japanese, they are trying to improve their robot is to work in, let's say, outdoor, rainy and all that kind of stuff. They need to get a better closing of the cage and all that kind of stuff. And they have to list it, they have to test it out and see whether the temperature and all that kind of. So I don't know exactly, I mean, what's the industrial standard for doing it, but then the HRP4 was supposed to be working in a dusty environment and also maybe a little bit water is fine.
I think you can go in two different directions, right? If, for example, you have a very specific mission in mind, then maybe you don't want it to be humanoid. Like for example, the imaging that they're doing in the floor, it's a cylinder, right? So it's far from being humanoid. I think you get humanoid when you talk about them interacting closely with humans. I think that's why maybe it creeps some people out that it's like human, who knows, but anyway. So I think that I think there is a whole range of things possible. On the one extreme specialization, in which case you're not humanoid at all, and you're designed for one purpose, like the drones and things like that. Those are sort of like robots, right? And then the other extreme is when you talk about personalized robots, where maybe one day we'll be writing apps and for robots.
Well, I was thinking collapsed buildings, things like that. You wouldn't want that form. You'd want something that was
Right.
small, like
Which
you
can,
get through
a cockroach, like a
spaces.
cockroach, right? Which
Right.
can clamber
Yeah.
through things and so on, right?
Right. So usually people always like in the robotics communities are debating whether the humanoid had to be in human form.
Yeah.
And why not just build something that
Special.
satisfies, yes, and specific for specific tasks and all that kind of stuff. So there's always a,
You can go both
know,
directions, I think.
it's all discussion and there's no end to that, I mean, basically. So I still think that the future of the robot is more in the brain, cloud computing, big data, and all look at all this data. Okay?
Well, I believe, Marshall, we have a reception
Yes.
here. Is that right?
Yes,
So
that's approved. Please
I
have
think.
three more
Thank you.
conversations.
Thank you.
Thank you again.
Thank you. Yeah.